Underneath both of them is the same note, at the same frequency, and that is something we can measure rather than assume. Nobody would confuse the two. Here they are, one after the other. Duh. Same note, different instrument. That gap is the whole file. This is Foundations File 2 of the lab notebook, where we build the sound in Python and then measure whether the label is true. Subscribe and follow along, because whatever separates those two sounds is not the number we spent the last file learning to count. Frequency tells you how often a wave repeats. It tells you nothing at all about what the wave does inside one repeat. Here is a single period of each side by side. Identical width, because the frequency is identical, and completely different shape. The shape is what your ear was reacting to. There is a theorem that makes shape measurable. A wave that repeats and behaves itself can be written as a stack of plain sine waves at whole number multiples of the fundamental. Those multiples are called harmonics, and each one arrives with two separate properties: how loud it is and where in its own cycle it starts. Which harmonics are present and how loud is what your ear reads as timbre. Where they start changes the picture far more than it changes the sound. Here are two stacks with identical harmonics. The third one, turned upside down, shifted by half of its own cycle. So here is how I build them, and it is the same shape of recipe as last file, with the middle step opened up. Step 1, the timeline, the same 44,100 moments per second we built before. Step 2, something riding along that timeline, and this time what rides is the variable. Step 3, the measurement. The sine is the one we already have from last time, and it is the only shape with a single harmonic. That is the whole reason it sounds the way it does. Nothing is plain about it because it was simple to write. It is plain because there is exactly one thing inside it. Here it is again. The square is that same sine hardened. Take the sine of it. Everything above 0 becomes +1. Everything below becomes -1. That is the entire change, one function wrapped around the line we already had. Same timeline, same frequency. Listen to what that one function did to it. And a triangle for a third point of comparison. The arc sine undoes the curve of the sine and leaves straight ramps running between the turning points, which is all a triangle really is. Notice the one thing we have not touched anywhere in this file. The frequency variable never changes. So listen to this one knowing that the note underneath it has not moved. 3 shapes, 1 number, and so far not a single measurement to explain why they sound different. If you want the explanation rather than the adjective, a like helps this reach the next person who was told that a waveform sounds warmer and never got a number for it. Here are all 3 in a row at 528 Hz. Sine, then square, then triangle. Now the instrument. We take the FFT of the square, which sorts a sound into the frequencies inside it, and the answer is not one spike. It is a staircase, and every step of it sits on a whole number multiple of 528. That staircase is the thing your ear was calling harsh, drawn out where it can be counted. And the staircase has a rule written down long before anybody measured this file. For a square, only the odd multiples survive, and each one carries a fraction of the fundamental's amplitude, 1 over its own number. A third of the amplitude at the third harmonic, which is minus 9.5 decibels. A fifth of it at the fifth, minus 14. The even multiple should be missing entirely. Minus 9.5 decibels measured against minus 9.5 predicted. Fifth, minus 14 against minus 14. The rule holds to the decimal place. And the even harmonics, the ones the theory says should not be there at all, sit 76 decibels down, about 1 part in 6,000. Subscribe. Every file here gets exactly this measurement before any claim is made. But 1 part in 6,000 is not 0, and the theory said 0. So where does it come from? Not from the instrument. The same measurement on a pure sine reads 238 decibels down, which is only the arithmetic noise of the numbers themselves. The real answer is that the sampled square does not repeat at 528 Hz at all. 528 and 44,100 share a common divisor of 12. So the pattern of samples only comes back around 12 times a second. And what the transform sees is a comb every 12 Hz rather than a clean harmonic series. I learned that the hard way. My first measuring window was 14 Hz wide, and it caught a comb line 12 Hz away instead of the harmonic I was aiming at, then reported it as the answer. Widening the window found something worse, and at a higher note you can hear it without any of this. Here are 2 squares at 3,000 Hz. The first written with that one sine function, the second built only from partials that fit. That low tone you just heard is not in the note. It is the 15th harmonic at 45,000 Hz, folded back down to 900, 2 octaves below the note being played. A square has harmonics forever, and everything above half the sample rate folds. Back at 528, the loudest fold sits at minus 33 decibels, 40 above the even harmonic I started with. The thing I was calling the artifact was not the big one. 2 tests. Double the sample rate and the folds drop 6 decibels every single time. Minus 33, minus 39, minus 45, minus 51. Not luck. The first harmonic that no longer fits doubles its number, and a harmonic twice as high is 6 decibels quieter. Then build from sines that all fit so nothing folds and no edge is placed, and it drops to 236 down. Here's our square one more time, now that you know what is inside it. Which means the whole thing runs backwards. If a square is nothing but odd signs in that proportion, then adding those signs should build one. Start with a single harmonic, a plain tone, sitting 0.44 away from the real square, on a wave that swings between -1 and +1. 2 harmonics, 0.32. 4, 0.22. 8, 0.16. 16 harmonics in, 0.11, and it is unmistakably a square. 32, 0.08. The difference keeps shrinking for as long as you keep adding. But look at the corner. That overshoot, about 18% above the flat top, does not shrink at all. It gets narrower and never gets shorter. That is Gibbs. And where you have seen it quoted as 9%, that is the same spike measured against the full jump instead of the top. Here it is, arriving out of nothing. So what is timbre not? First, it is not the note. All 3 of the shapes we have built measure a fundamental at 528.00 Hz. Ask the instrument what note is playing, and it answers the same thing 3 times, because by note they are identical. The note is the bottom step of the staircase. Timbre is everything standing above it. Here they are again. 1 note, 3 instruments. Second, more harmonics is not more volume, and this is the one that caught me while I was building the file. Built to the same peak height, the square carries 3 decibels more energy than the sine. That is a real difference, but it is a difference in crest factor, which is how tightly the same energy packs itself against the peak. It is not evidence that harmonics add loudness, and the 2 stacks you heard earlier settle that. Identical harmonics, and one of them peaks half again as high as the other. So we matched by energy instead. Matched that way, the square's own fundamental sits about 1 decibel below the sine's. Same energy spread across more steps. Here is the same sine twice, first against a square at equal peak, then against one at equal energy. Third, and this is the one that gets sold, none of these is better. Not richer, not purer, not higher quality, and nothing about the shape of a waveform makes it good for you. What we measured is a distribution of energy across a staircase, 6 numbers for the square and 6 different numbers for the triangle, with the same note underneath both. That is a complete description of a steady tone, and it is the entire claim the physics supports. A real instrument also changes while it plays, and that is a separate file. One more because it makes the rule visible. The sawtooth is the 4th shape, and it keeps every harmonic, even ones as well as odd ones, each at 1 over its own number. Its second harmonic sits at -6 decibels, right where the square had an empty step. Same fundamental, same 528 Hz, and a completely different instrument. Here is what a full staircase sounds like. Your turn, and it is 4 lines again. Build a square at 528 Hz, at 44,100 samples per second. Take its FFT and read the level at 3 times the fundamental and then at 2 times. Read the exact bin, not the loudest thing near it, or you will make my mistake. You should find -9.5 at the odd one and about 76 down at the even one. Then change the frequency and run it again. The -9.5 will not move from 100 Hz up to 1,000 because it is a law. The even number will move, and you can predict where before you run it. Take the greatest common divisor of your frequency and 44,100, and that is the spacing of everything the grid adds. Put both numbers in the comments with the frequency you used. One number is a note. A stack of them is an instrument. I build these sounds from scratch and then I measure them, so that nobody has to take my word for any of it. The recipe and the verification are both on screen, and you can run the numbers yourself. That includes the 2 numbers I got wrong first. The loudness comparison was backwards until I matched the waves by energy, and the even harmonic was the wrong bin until I stopped measuring through a narrow window. Both corrections are in the version you just watched. If that is worth something, 3 small things genuinely help. A like, so this reaches the next person trying to check a number. A subscribe, because every file gets this same measurement before any claim is made. And a comment with the level you measured, so the next person has something to compare against. Next file, the instrument itself and how one calculation can hear 3 tones at once. Sound measured.